So this video, we're looking at the waste outcome direction of conventional current. Okay. So just from last year in year 11, we remember that we looked at conventional current and electron current. Okay, and electron current. Okay, so electron current is the way is what electrons actually do in a circuit. Now, it turns out when we made these laws a long time ago, when they were first thought up, we thought that it was actually positive particles doing the moving, and so we made up all of our electricity laws for positive charges. Now, it turned out when we investigate further that actually it was electrons actually moving around a circuit. Okay. And so we were actually doing it was actually the opposite way around. So anywho, so conventional current is positive to negative. Okay, so if you have a circuit, it's positive to negative. So we've looked at this idea in quite a lot of detail. Okay, so if you have a positive and a negative plate, okay, and you have a circuit here, this is your negative end and this is your positive end. I always remember it that it's the shorter one here that is negative, because a negative sign is a shorter sign. Okay, so the shorter side is a negative, and it looks like a negative too, if you draw it that way. They both look like a negative, but anyway, that's how I remember it. And the positive side is the longer end. Okay, I just went and checked that was correct, because I always get these wrong, but I am right this time. So that is the negative end, that is the positive end. Anywho, so if you're looking at conventional current, I will put conventional current in red. Okay, so I'm going to draw this in red, and the electron current, we're going to go in green. Okay, so the electron current, we're going to go in green. So electrons actually move from the positive end to from the negative end to the positive end. So this is how my electrons move. Okay, but conventional current, we say, goes from positive to negative. Okay, so this is my current I. If you remember from last year, it's capital I. Okay, and the current is in amperes. Okay, and current is the flow of charge per unit time. So remember that that current is the flow of charge per unit time. Okay, so if you imagine a pipe, the more charge is flowing through. Sorry, that's a really bad view of charges. But let's say the more electrons flowing through this wire at a given time, the more the current will be. Okay, so the current is proportional to the number of charges flowing through per unit time, or the rate, it's equal to that. It's equal to the rate of flow of electrons or charges, and in this case, it's going to be electrons in our case for a circuit. All right. So there are two. So that covers the conventional current side. There are two types of circuits or currents, which is direction current and alternating current. We'll talk about that later. I won't go into that today. Okay, and we might as well cover quickly this waste outcome too. So we figured out that conventional current is the flow of electrons from positive to negative, and electron current is the way negative charges flow, which is actually from negative to positive in a circuit. So this outcome is that the voltage, okay, can be thought of as the work done per unit charge. Okay, so if you remember from last year, we talked about voltage, or we use another word. We talked about a difference in potential being similar to a difference in height. Okay, and if you want to bring, so if you think about this potential energy, if you think about this as potential energy and at both points, right? If you want to take a basketball and you want to raise the potential energy of it, you've got to do some work on that object. Okay, so work is in joules. You've got to give that object some energy. Okay, so that's the analogy of a height difference. Excuse me. So that's the analogy of a height difference. So a potential difference for a circuit is the same thing essentially. When you've got a cell, you've got a part that's positive and a part that's negative, and there is some potential difference. There's some difference in charge between those two sides. Okay, and then when you connect them up with a wire, the two sides cancel out, and this is similar. This is very similar to what happened with the spheres touching. Okay, the charges cancelled out, and they became the same. Okay, so they became the same, and the potential difference was eliminated, or the potential difference became zero. Okay. Anywho, so if you increase the potential of a basketball, you're applying some work. Okay, so we know voltage is a potential difference between points, and this is the amount of work that you do per unit charge. Okay, so if you that's the definition of work done, of voltage. Okay, and voltage is measured in volts. Okay, so it's work done per unit charge, and work done is in joules. Okay, charge is in coulombs, and so you get that a volt in its SI units is a joule per coulomb. Okay, that's what a volt is. Okay, so a volt is work done per unit charge. So this is a key formula, the same as how current is the flow of charge per unit time. Okay, so that's another key formula. Alrighty, so here you notice that there are some formulas that you can kind of shuffle around with this, because voltage is work done per unit charge. Charge also shows up in this equation. So if I wanted to substitute this current and time for charge, I could actually do that, and so it would give me that it would be work done divided by T times I is actually Q in this, so it's IT. Okay, so there is, so it gives you this equation, which voltage is the work done divided by the current times the time, or you could rearrange that to say work done in joules is equal to current times time times voltage. Okay, or ITV. That's an easy one to remember. There's a channel in the UK called ITV, but you guys probably wouldn't be aware of that. But anywho, okay, so that's how that's derived. I don't think there's really too much for me to talk about here, and so we'll move on to the next part. Okay, so that's just a formula. It's pretty easy to use. This is an interesting one. Okay, so waste outcome. A positively charged body in an electric field will experience a force. Well, that's obvious. Okay, so it's the same as a mass in a around another mass will experience a force due to the gravitational field. So this is saying a positively charged body or negatively charged body will experience a force if put in a field. Okay, so what is this force that it might feel? Okay, so the electric field strength is similar to the gravitational field strength. So in gravitational field strength, you had it was the force per mass, and then if you rearrange that formula, you get your force due to gravity is your mass times your gravitational acceleration. I'll leave the A out. You don't need that. So for an electric field, it's a similar field. So it should really be the force per, not unit mass, but per unit charge. Okay, so the electric field strength is equal to the force divided by unit charge. Okay, so that's what this is, and you can further say that it's the potential difference divided by the distance between the two objects. So this is often used for charge plates. So this whole E is equal to voltage divided by the separation is often used for charge plates. So maybe this is something you might want to add into your hints and tip sheet or your mind map to say that this is typically used for charge plates. And I'm going to quickly draw up how it is used in charge plates. So you might have a positive plate here, you might have a negative plate here. There is obviously a difference in potential here, and the electric field strength, if you were to say what is the electric field strength here, of this field, what's the field strength? That would be your voltage or your potential difference divided by the distance of the plates. Okay, and then so this is in volts per meter. Okay, that's the so electric field strength is in volts meter minus 1, and excuse me, and where was I going with this? So if I put an object of I don't know if I put some charge here, what would it feel? Or if I put a charge of positive 1 nanocoulombs in this field, what would it feel? So you can actually use this electric field strength equation to say, well, this is the force per unit charge. I can input the charge of positive 1 nanocoulombs. If I know the voltage between the plates and I know the distance that they're separated by, I know the electric field strength, and then I can calculate the force that this sphere is feeling. Okay, so these equations, I just want to note that they're often used to calculate the force on a charge between two charged plates. Okay, this is a common question in the WACE. This is quite a common question in the WACE because it requires you to use a couple of formulas and to use this kind of that equation there. Okay, this is quite a common question. All right, so I'm actually gonna scroll right down to this section here. Okay, and we'll do an example. And really quickly, it's important to note that you should really know the charge on an electron and a proton. So the charge on an electron is negative, and the charge is 1.6 times 10 to the minus 9 coulombs. This is in your data booklets as well. And the charge on a proton is positive, the same amount of 1.6 nanocoulombs, or positive 1.6 times 10 to the minus 9 coulombs of charge. Okay, so that's what that is. Let's do a quick example, and then you don't have to hear my voice. So I'll give you these notes. This is just a way of working out of deriving another formula. Okay. Okay. Alrighty. So determine. So there's two charged parallel plates placed 10 centimeters apart, and there's a potential difference of 240 volts between them. The first question says, what's the electric field strength? So we know that the electric field strength is the potential difference divided by the distance between them. By the way, if you would like, you should probably pause the video beforehand and work it out yourself. So and then check your answers with me. So this is 240 volts divided by 0.1 meters away. Okay, so and that gives you, and I always put this in my calculator in exam conditions because I always get things like this wrong when I try and do mental calculations. So always do this by yourself. Always put this in the calculator yourself. That's 2,400 volts per meter. That's the electric field strength. Okay, there's nothing else. We don't need to put positive, negative, anything like that. If an electron is located halfway, that's a keyword, so I'm going to underline it. What force would it experience? Well, I know that my electric field strength is the force per unit charge. Now, I already know what that is, so that 2,400 is equal to the force that this electron would feel divided by the charge that it has, which is negative 1.6 times 10 to the minus 9 coulombs. Now, I actually don't know what to do with this halfway section. I don't know how that is relevant. Because the electric field would be constant. That's an interesting one. So you've got a positive plate here, you've got a negative plate on this side, you've got an electron here. So it would feel a repulsion because of there, and so the electric field would be going this way, pushing that electron. Sorry, the opposite way around, obviously. Sorry, I'm completely wrong. It would be acting this way, okay, to try and push the electron to the positive terminal, okay. So I think the force should be on the electron should be 2,400 volts per meter times by negative 1.6 times 10 to the minus 9, which would give me which would give me 3.84 times 10 to the minus 6 newtons. Okay, that's what it would give me. Okay, I'm just going to quickly check the answers to this actually, because I don't want to give you the wrong answer. So let's just quickly check the answers, and then we're done for this video. Scroll through this part. Electromagnetism, workbook 1, and it's the key. And we're scrolling all the way down to the force halfway between the plates. So 2.4 times 10 to the 3, and then they got the force is the electric field strength times. Yeah, so they got the same thing, I think. 3.84 times 10 to the minus 6, minus 16. Oh, right. Okay, so sorry, it isn't nanocoulombs. That's my bad. So I am actually wrong. This is minus 19. And so if you go up, sorry, so the charge on an electron is minus 19. Minus 19. We go up. Oh, so I did this wrong. So it's not minus 9. It's not nanocoulombs. Okay, it's times 10 to the minus 19. So it's a lot smaller. Okay, so it's times 10 to the minus 19. Sorry, they had it right. Thanks, guys. So the answer is off by a factor of 10 to the 10, which is huge. So actually, this should be to the negative 16. Okay, thanks, guys. Have a good one.